Hello 112 students. I wasn't totally happy with the way that I covered Raoult's law in class, so I wanted to provide this additional video to help you guys out. Raoult's law states that the vapor pressure of a solution is a weighted sum of the vapor pressures of the solution components. Let's look at that mathematically. The vapor pressure of our solution is the sum of the contributions of each component. This sigma here just stands for summation, so you can expand this out and add a term for each component of the solution. Each term consists of the vapor pressure of the pure component, that's the P sub n, and the mole fraction of that component. Recall from class that the mole fraction, chi sub A, is equal to moles of A over the total moles of stuff present. Let's calculate one. Example, you make simple syrup from 50 grams of sucrose and 50 grams of water. What is the mole fraction of water in the syrup? You can pause the video now if you want to work this out on your own. To begin with, you'll convert both of your masses into moles. So 50 grams of sucrose becomes 0.146 moles of sucrose, 50 grams of water becomes 2.77 moles of water. Then we can just say that the mole fraction of water is equal to the moles of water over the total moles present, or 0.949. Let's keep moving. With non-volatile solutes, so non-volatile means this solute has very low vapor pressure under normal conditions. You may assume the vapor pressure of a non-volatile solute is 0. It does not contribute to the vapor pressure of the solution, but it does suppress the vapor pressure of the solvent. Consider some pure solvent. You can see that we've got molecules in the liquid phase. We have molecules at the liquid-gas interface. This is where they stand a chance to escape into the gas phase, which is what we see up here. Now let's say we add a non-volatile solute. So these solute molecules are going to get in the way. They're going to crowd the interface. If they crowd the interface, there are fewer solvent molecules at that interface, and fewer of them get the chance to escape into the gas phase. This is how non-volatile solutes depress vapor pressure. Let's look at an example. The vapor pressure of water at 25 degrees Celsius is 23.8 torr. What is the vapor pressure of the simple syrup you created on the previous slide? Well, since we can ignore the sucrose contribution, all we need to care about is the water. The vapor pressure of the solution will be the mole fraction of the water times the vapor pressure of pure water. We plug in our mole fraction from the previous page and the vapor pressure from the problem, and we get 22.6 torr. Now note, the vapor pressure of sucrose is 0. So the mole fraction times the vapor pressure of sucrose also equals 0. This is why we only see the water. But not all solutes are non-volatile. Now what about volatile solutes? Volatile solutes have a non-zero vapor pressure under normal conditions. Most liquids fall under this definition. So let's consider a thought experiment. Here is a beaker full of pure A. A has a reasonably high vapor pressure. You can see that we have a lot of molecules up in the gas phase. And now let's consider pure B. B has a lower vapor pressure, and you can see that because it has fewer molecules up in the gas phase. Now what happens if we mix these two together? If we mix A and B together, we're going to have a mix of A and B molecules at the interface between the liquid and the gas, and that's going to affect how many of them get up into that gas phase. Now, because all three of our beakers are under the same total pressure, we have the same number of total molecules in the gas phase, but what's different is which molecules they are. Take a look at pure A. Pure A has 8 molecules in the gas phase when it's pure, but it only has 6 in the gas phase when it's mixed. Similarly, pure B has 3 molecules in the gas phase, whereas in the mixture we only see 2 of B. The same total number of molecules is there, but there are fewer molecules of each present. This tells you that each component contributes to the overall vapor pressure, but that individually their vapor pressures are lower. Time for one more example. A specialty fuels company produces blends of octane and hexane as a high-performance gasoline. Using the information below, calculate the vapor pressure of their violet label product at 20 degrees Celsius. So it contains hexane at 85 mass percent and octane at 15 mass percent. Whenever you get given a mass percent for a composition, your starting assumption should be that you have 100 grams of whatever it is. So we're going to assume we have 100 grams of gasoline. This is great because it means that these mass percents automatically become masses of our components. So we can convert both of the components into their molar amounts, and we can total up the total moles of stuff present. So now that we know the individual moles and the total moles, we can calculate mole fraction, and because we have the vapor pressures, we can plug this all in to Raoult's law. So the vapor pressure of the solution equals the contributions of the hexane and the octane. So in our hexane term, we've got the moles of hexane over the total moles times the vapor pressure of hexane. In the octane term, we have the same thing going, but for the octane. If you crunch your numbers down, you get a final answer of 110 torr. So there you go. That's Raoult's law. Just remember, you have to keep an eye on your mole fraction and your vapor pressure. So good luck on your homework and your exams, and I will see you guys next class.